I work for HBC Digital, and I'm going to talk to you today about concurrency and specifically some strategies to handle concurrency, reactive, and shared state. So a little bit about me. I'm a developer. I like to rock climb. I'm a dad, and I'm a Scala junkie. I'm really into the language right now. It's just absolutely gorgeous. It's fun to work with, and HBC Digital does a lot of Scala, and that makes it awesome. HBC Digital, we're a division of HBC, the Hudson Bay Corporation. It's the Macy's of Canada, they like to call themselves. We have 4 banners: Hudson Bay, Lord & Taylor, Saks Fifth Avenue, and Saks off Fifth. Each one of them has their own e-commerce site. And we have a really strong engineering culture and some really good staffs. So it's, again, a really exciting development place. Concurrency, multi-threads executing simultaneously. So basically multiple things trying to do jobs at the same time. Today we're going to be looking at kind of a hypothetical inventory application. And the challenge with a concurrent inventory application is to make sure that you don't sell something, or to make sure that you don't sell things that you don't have. So to make sure that that when you say that you're selling something to someone, that they're able to actually buy that inventory. So so concurrency, options to handle concurrency. So the two we're going to be looking at today are shared state and Akka. But there's some other things too that we could look at. There's like functional reactive programming, which is where you have streams of information. You can compose those streams and modify them and make other streams. The values kind of change over time, and you can kind of constantly broadcast them. It's a really cool kind of conceptually, and there's like some languages out there like Elm that use it that are kind of something that you could put into production. But for the most part, it's a bit more tricky to be able to do something that talks in 2 ways. There's publisher-subscriber like JavaScript event handling. Communicating sequential processes is similar to an actor framework, except that it's sequential, it's not asynchronous, and it's anonymous processes. And software transactional memory, as the name implies, is essentially analogous to a database transaction. Okay, so shared state. Shared state is where immutable state is shared across the application. Shared state uses things like locks and synchronization to make sure that you don't run into race conditions, that only one thing can modify a particular piece of memory at a time. It's proven, it's well understood, it's been used forever, it's kind of the go-to that's been used for a very long time, and a lot of developers know how to use it. So those are kind of the benefits of it. For very trivial applications, it's simple to reason about. You're able to kind of just lock something, then something has to wait to access it. But when you run into situations where objects can get locked and then need to access other objects that could be locked, you could run into deadlocks. Both of them are waiting for something else to release a lock, and then you can run into issues. And then the big problem with shared state is that putting threads to sleep and waking them up while they're waiting for access to this code can be very expensive. Context switching, there's a lot of things going on there that are really expensive operations that shouldn't really, that don't have anything to do with the code that you're writing and are really uncontrollable. So that's kind of an issue. Akka, reactive, and actor framework. So it uses actors instead of threads. They're kind of analogous, except actors are much lighter weight. You can think of an actor as like a person. They have one job. They can do one thing at a time. Each actor has a mailbox. Actors send messages to each other. And these messages are asynchronous. They're sent out, they're objects, and an actor processes these messages one at a time. Essentially, their mailbox is a queue. So you don't have to worry about concurrent access because only one message is being processed at a time, and the mutable state that you have is actually stored within an actor. So if I'm an actor and I have a value that I'm changing, no one else can change that value, or shouldn't be able to change that value if you are designing your application correctly. And as I process my messages, I'm changing the value. Maybe if 2 people ask me for inventory, those are 2 separate messages. They're handled one at a time. So whoever gets there first would get the inventory. The other person is going to have to buy it somewhere else. There's very loose coupling. The method that the actor uses to receive its messages can handle any type of object at all. So you can pass anything that you want to an actor. You don't have to really have any knowledge about what's going on inside. But again, you have to really worry about how you're modeling and how you're thinking about like your application. So you really have to worry about like resiliency and performance. So you have to think about how you can multi-thread, which isn't always simple because since you can't share immutable state, when you run into an issue where you want, say, multiple actors to be able to process inventory requests, you have to think of a way of farming out that work so that each actor is responsible for some of the work, but isn't actually going to end up changing state that some other actor is changing. So in this case, we're going to see that what I'm doing is having one actor per product ID. So each product has a single actor that takes requests. So as many products as you can have that many actors changing the state of those products, the amount of inventory, but you don't have to worry about multiple actors, running into concurrency issues. One other thing to think about is supervision. So if an actor is very important, they have mutable state that you don't want to lose, then you want them to have children that are handling complex operations that can fail. So that actor can supervise that child. They can restart if they need to, but if there's failure, then you don't lose the state that's stored in the actor. Okay, here's a diagram of what this application is going to look like, the Akka application. So essentially what's happening here is we have clients, they're making requests to a router, and so when someone requests a change to the inventory, they're calling an actor called an inventory updated. That actor is responsible for that one particular product ID, and is the only thing that can change that product ID. But it's pretty quick because all he's doing is updating that information and then returning a response back. So in the top case, if he gets a request for enough inventory that he actually has, he sends a response back that says, okay, you successfully requested 5 pieces of inventory, I'm going to give that to you. And then there's other actors that are actually responsible for the other half of this, where they're actually returning responses to people that just want to know how much inventory we currently have. So once that actor updates the inventory that he's controlling, he sends a message to that pool of getter actors and says, okay, I've just decremented my inventory. You need to decrement your inventory as well. And then when someone makes a GET request, they're not hitting him, they're hitting all of those actors down there. So in that way, we're able to handle concurrency. We're able to have a pool of 10 actors responding back to these requests instead of having that one actor handling both the update and the GET request. So that's pretty much how we're gonna model it. All right, a quick slide about DevOps. HBC, we're very focused on DevOps right now. We're using all these technologies right now, and the benefit of using things like Vagrant, Puppet, Docker is that you can practice infrastructure as code. So now when we make a change to infrastructure, we can version it, there can be pull requests, it can be reviewed, and once you've made that change and you have like a chef recipe or using Puppet or Docker, it's reproducible over and over again. You know exactly what you're getting every single time. If your developer is developing on that platform, you know when you move that container into production, it's exactly the same. You don't run into weird issues where something happens in production that didn't happen in your test environment. All of that. So it's a very exciting time to kind of be a developer because now you get to take on more responsibility for infrastructure. You get to own your code into production, and it's really cool. On the right side is some of the stuff that I'm using in this presentation. I have a GitHub repo set up that has all of the code and the environment actually to run the code. So if you follow the README, you do a few steps, you'll be able to do Vagrant up, bring up a virtual machine, a Linux virtual machine, have Graphite installed, Docker, SBT, Java, everything running, and you can run your applications without having to install all those things, and all those things work. So, okay. So, sure. Yes. I absolutely am. It's public. You're going to have access to it. You can do whatever you want with it, and I'll be happy to answer any questions about it. I'm happy to answer questions now, but if you start playing with it after this and you have any issues or have any questions, please, my Twitter handle's on there. You can ask me anything. It's completely open and completely available. Yes. So these are the things that I'm sharing amongst the two applications. So the thing that was important for me was the concurrent access to the inventory. So that's the part that's different, but at the same time, we need to have a web server. We need to be able to persist information to the database. We need to collect metrics. So these are all being shared by both applications. So we're using Plague, which is a web framework built in Akka. It uses the Netty web server, which is kind of developed by JBoss. It's a non-blocking, very lightweight web server. We're using Reactive Mongo, which is an asynchronous MongoDB driver. It's very cool. It immediately returns back a future, and then that future can resolve or not as to whether it actually succeeds. But completely non-blocking. So you're going to see non-blocking a lot. Everything's non-blocking. The web framework's non-blocking. Reactive Mongo is non-blocking. StatsD, the aggregator for our metrics, is completely non-blocking. We send messages via UDP. There's no response whatsoever. You send out the message. If you lose a metric, who cares? That's not part of the application. But you don't want to wait for a response coming back, from your metric. You don't want the customer to have to wait for that. So you send and forget, and then StatsD aggregates, sends it to Graphite, and we'll be able to see all of the metrics that we're collecting on graphs in Graphite. Okay, so here's a little bit of code. I'm not going to go through all the code. I don't really have time. All the code's in the GitHub repo. It's all public. You'll be able to see it. Ask me questions about it later. But just a few things that are kind of important. So as Nicolette asked about before, we're using tree maps. Tree maps, I think, are sort of like state of the art right now in terms of what you can use for a map, hash map, basically, structures that are completely concurrent. You don't have to worry about what's going on there. So what we're doing is we have a model called inventory quantity. We'll look at that later. And essentially, we're generating 100 random products, giving them inventory from 10,000 to 20,000, putting them into this tree map, and persisting them to Mongo. So this is how we will initialize the application. This is one of the handler methods. So play has a routes file. You specify the HTTP verb, you specify the route that you want, and then you specify the method that responds to that route. So in this case, this is the update inventory method. If you make a put request with the right URL, you'll get this method. The product ID is the first parameter. The amount of inventory that you want to get or put in is the second parameter. And again, action.async, this method is completely non-blocking. It immediately returns a future. The request thread or actor waits for the response, but it just shoots right through here, completely non-blocking. So what are we doing here? So the first thing we're doing is we're collecting the start time. So the start time is going to be for our metrics. We want to see how long it takes to basically run this method. The next things that we're doing are we're looking up the model for this particular piece of inventory, and then we're calling update quantity on this method. So essentially, we're looking to see if we can update the quantity, and inside of that inventory quantity is where we're going to be doing our locking. So everything in this method should be completely non-blocking, should be completely just available. Any thread should be able to get this information, and we'll see the locking later on. And then we're persisting to Mongo if necessary. And then you see this thing in the bottom here. We say f.onComplete. So that's a callback. That's for our future. Once the future completes, then we send our metrics off to StatsD, to Graphite. So we don't want to wait until the method finishes because that happens immediately. We want to actually wait until all the processing is done. We want to see exactly what's going on before we actually send our metrics. So that's what's happening at the very end there. And then here's our inventory quantity model. So this is actually where the locking is happening. This is the update quantity method. So apples to apples, you saw in the model that we use for Akka, you could have dirty reads, right? So you update the quantity, and the message gets sent to the other actors that are giving you back your inventory. If you ask for that inventory before that message gets to that actor, you might be out of date, which is not the worst thing in the world. That can happen anyway with latency. That can happen after the page is already loaded. You don't need to necessarily have instantaneous access to the inventory. Similarly, for our shared state application, when you get the inventory, it's not here, but when you get the inventory, it just immediately gets the inventory. We're not doing any read locking. We don't care if you're updating the information. We're just going to give you back instantaneously what quantity is available now, just so that we're responding quickly. But what is happening here, when you update the quantity, we're implementing a write lock here. So we lock this method here. A thread comes in and wants to update the quantity. We lock all the other threads out. They go to sleep, and then once this thread is done updating information, it leaves. Now it's unlocked. Now the next one can come in. So this is basically the crux of the whole thing here, right? This is where we're doing our locking. This is the only thing essentially that's different between this and the actor model is this one little piece of code right here. And this is we're going to see how it performs. Okay, so that's just the shared state application. Now we're going to look at the Akka application, the reactive inventory application. So the first thing to note is we're creating an actor system. So Play has its own actor system. Play is built on Akka, and there's an actor system that already exists for handling the HTTP requests and doing all the things that Play needs it for. We've had some discussions internally about whether or not we can reuse this the actor system. I honestly haven't done a lot of benchmarking in terms of that, but apparently actor systems are pretty heavyweight. But in this case, I haven't seen a performance improvement either way. So I'm creating my own actor system that's just handling the inventory. So what's an actor system? It's essentially an environment where there's an actor hierarchy that shares resources, that basically is like a kind of a sandbox for all the actors to live in. So then the next thing I'm doing here is I'm initializing the actors, similar to what I was doing in the shared state application. This isn't a really realistic application. If you have more inventory to, a new piece of inventory to add, a new product, you can't do that with this. This is just like a toy here. So we're just going from 1 to 100. Those are our products. And then for each product, we're giving it a random quantity of inventory, and then we're creating an actor, an inventory updater actor. We're putting that into a tree map, and then we're creating 10 inventory getter actors. And those are going to be the actors that just retrieve the inventory. So we have one actor that can update the inventory, but 10 actors that can get the inventory. So that's kind of important, right? Because the shared state isn't happening here. There's only one actor that can do any updating. We don't care how many people are actually able to get it. We saw that with the other shared state application. This is kind of the way that we're doing things. So we create at the bottom there. What we're doing is we're creating a round robin group. So essentially that's a router. So those 10 actors are getting, as 10 requests come in, it's going one to each actor until so that we're farming out those requests. We're able to basically concurrently serve that information without having too much issues. So there's one really interesting line here that I want to highlight, which is this top line. So this is our first message that we're seeing that's being sent to an actor. The exclamation point right there is Scala syntactic sugar that says tell. So what this is saying is, I want to tell the inventory updater actor this message, and this message is an object. All messages are objects, and this message is an object that's a register listener object that's passing a value that's a rowdy, which is another actor actually. So what's going on here is we need to be able to tell our getter actors when we've updated the inventory. So we're kind of using like a publisher-subscriber piece right here. So we're basically keeping a vector inside of the inventory updater. When we say register listener, we're adding an actor to that vector, and then once the inventory updater updates inventory, it'll send out messages to every single actor in its vector that says, I've just updated myself, you need to update yourself too, so you have the correct amount of inventory available. So similar to the shared state application, we have handlers. This is our update inventory handler for the reactive application. And it's very similar to the other handler, with the exception that it's a little shorter because some of the work that's being done on the shared state application in the handler is actually being done in the actor for us. And it's not a huge savings in terms of code to be able to use Akka. That's not really the point of Akka. It's a lot more about the ability to model things in a really nice way, the ability to handle concurrency this way, the ability to really, it's just a different paradigm. But it's not about like less code or, it's more about being functional. It's more about being able to reason about very complex systems. So again, same thing. We start the timer. We get a future back. So now here's the next very interesting thing. There's a question mark at the end of that third line. That question mark is another piece of syntactic sugar. That's another message that we're sending. That's an ask. So the other one was a tell. This is an ask. An ask creates a future by sending a message to an actor and waiting for that actor to send a message back. So in this case, we're looking up the actor that's the appropriate updater for this product ID. And we're saying, I want to know if I can buy this much inventory. So we're sending a message, an updated inventory message to that actor, and then you can see that map to, we're basically getting back a future of any or something along those lines. That's not typed, so we need to type it to a result, but we're getting back a result that we're then going to be able to pass back to the HTTP requester. And similarly to the other application, once it's finished, we have a callback here that's saying when that future completes, once it's done with its work, and I've now gotten a response back, now send the stats off to StatsD so that I can see how long it took. Okay, so this is my last slide, and then we're going to look at some code. So I'm going to try and go quickly. This is a little more information, so it's going to take a little longer. But this is most of an actor. I've kind of I've put some dots here because it's too much code for one slide. But essentially, this is the inventory updater actor. So I say event source at the top there. The reason I mentioned event source is a trait. When we're creating actors or any object in Scala or any class, you can mix in traits. And so what a trait is it's like a piece of functionality that might be used by multiple classes. So in this case, we have an event source trait. That event source trait is the trait that's responsible for being able to register other actors to receive messages when I want to send it. There's a method call down there, like about 4 lines from the bottom, that says send event. When I call send event, that's going to send that event to all of the actors that have registered as listeners to my event, basically. So how does it know when to register those actors? We'll get to that. That's the last line there. There's an event source receive. We'll explain what's going on there. But that's what's going on there. So the inventory up there. The first thing up there is a companion object. The companion objects for actors, usually the pattern is that you create a companion object, and that contains all of the messages that this actor is going to be dealing with. So in this case, we have an update inventory message. That's the only one that we have. And now we can use that, that message basically within this actor and any other actor that gets messages from this actor by importing that object. Okay, so the class definition. So there's the class line right there. That's passing in constructor parameters. That's setting the state for this application or for this actor. This is the product ID. This is the quantity that we're starting out with, and here's how to get in touch with Mongo. The next line is the method that's going to actually call Mongo. So this is actually calling set inventory on the set inventory that's actually doing an update in Mongo. And again, completely non-blocking. It gets back a future. Doesn't really do much with it right now. It ends up basically logging it if there's an exception. But essentially, just updating the inventory within Mongo. Next line is the one that actually initiates the first Mongo request once we actually create this actor to actually set the initial inventory. And then we have this def inventory receive, which is a type receive. So every actor has a receive method. And in this case, our receive method isn't just one method. We're actually joining together 2 methods down there with that or else. So what the receive method is it's a partial function. In Scala, a partial function is like a switch or a match statement that has cases, and you're basically defining which messages this actor can listen for. So in the case of this actor, we have 2 receives. We have the receive from event source that's going to register and unregister our listeners for the send event, and then we have the actual work that this actor's doing. And the cool thing here is that if we had 10 different kinds of actors, all of them wanted to have event source functionality, we could do the same thing for all of them without writing an extra line of code. We would just basically join in the event source receive method along with whatever receive method this one has, and then it would be able to handle those messages as well. So what's going on in this method? So essentially, we're handling receiving that message type. We're checking if we can update the inventory. If we can update it, we send an event to all of the getters so that they have the correct amount of inventory for them for this product, and then we persist to Mongo. And that's it. Then we send a response, sender, exclamation point, OK. Now we're sending a response back to play to say, OK, we're done. Here's the response that you want to send back to the HTTP requester. This is the information that they want for what actually happened. All right, so that is pretty much that for the presentation. And now let's run some code. So the first thing that we're going to do is we're going to kind of look at like kind of the environment. So the first thing that we would have done if you were running this on your computer would be to go to the README, install, make sure Ruby was installed, make sure Vagrant was installed, make sure that the Vagrant plugins were installed, and you'd call Vagrant up. Vagrant up would download a whole bunch of stuff. Depending on how fast your internet connection is, it could take maybe 2 minutes if you're lucky, up to 40 minutes if you have dial-up access or whatever. So I've already done that. Vagrant's up, and you can see essentially I've created a machine on my computer. It's a virtual machine that's running Ubuntu and has all the stuff that I need installed on it. So so the next thing here, what I've done. So I've SSH. So if I'm in the root directory here, first of all, what's happened is when I call Vagrant up, it's going to mount my repo inside of the Vagrant box. So now all the code for my repo that I've cloned is now inside my Vagrant box and ready to run with the applications that are in there. So now by calling Vagrant SSH, there's an adapter that Vagrant provides. I could call the IP address for ETH1, 192.168.44.22. That's the actual IP for this box, and you'll see that I'm going to be referring to that in my browser. But it's kind of a shortcut. If you're in this directory, if you're in the Vagrant directory, you're able to do Vagrant SSH, and you just go right into the box. So then you can see I've CD'd to /Vagrant. Again, this is the mounted directory, reactive inventory. So this is a reactive application, and I've called SPT. So I started the Scala build tool, and then I've run start. So now I've actually started the application, and you can see I actually stopped it before and started it again. But you can see it's now running right now. So this application is running. The reactive application is running. And similarly, here's the shared state application. I've just run start 9001, so I'm just running on a different port. It's another application. So both applications are running together right now on separate ports. They're talking to the same Mongo database in different databases within that Mongo server, and they're just running. So, but you don't have to take my word for it. I'll show you that, right? So let's look here. So first thing we can do is we can call 192.168.44.22 port 9001 shared state inventory. I'm hitting the router. I'm making a GET request, and I'm actually getting the inventory for product ID number 1 for the shared state application. It's 14,042. That's running right now. Similarly, if I call in port 9000 reactive inventory, so different amount. It's not the same one. 14979, product ID number 1, reactive inventory. Now, we can do something a little cool here. So now we can actually make put requests with curl and update the inventory. So now we're calling port 9000, the reactive inventory. We're trying to reserve 5 of item number 1. Okay, we get a response back, success equals true. That actually worked. Again, we hit the play application hit our actor reserved that inventory, and hopefully send a message to all those getters to say, okay, update your inventory too. So we should see a difference there. We'll see that in a minute. And now similarly, shared state inventory. Okay. Okay, that's weird. It's compressing the. So obviously that put request, what you really say there is 192.168.44.22 / blah 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 blah. Because this is so big, it's being compressed. But take my word for it, that's calling the right URL, and has now updated the inventory for SKU number 1 by 5. So we've taken away 5 from each of the SKUs. So now back to our web browser, and now from 14979, we now have 14974. So we've updated the inventory here, 14042, 14037. Okay, but now what about Mongo? So now let's quickly go over here, and now we have our Mongo shell here. We're logged into Mongo, and let's see what happened here. So now we're in the reactive inventory database. We're looking at the inventory collection. We're asking for SKU number 1, and now we see 14974, which my memory's not so great. 14974, and now if we use shared state inventory, switch to the database, find 14037. So everything's all hooked up now. Everything's working properly. Okay, so now we're going to look at this. This is Graphite. This is the Graphite dashboard. This is getting metrics from our application. What you can see here is that this is the request that I just made. The top is the response time in milliseconds, and the bottom one is the number of requests. It's aggregated, so it's not really 0.1, right? But it's the number of requests per second. You'll see this like when we start running with more load. And this is kind of telling us exactly how long everything's taking. So now we're going to open JMeter. So I'm using JMeter basically to run my tests. Essentially, I have four calls that are being made here. I'm making a call to the shared state inventory on port 9001. And I'm passing, this is a GET request, I'm passing a SKU counter, so that's going from 1 to 100. It's basically just trying to get the inventory for every single product, 1 through 100, just like cycling through that. Reactive, same thing. Calling GET, port 9000 now, going through here. And then we have the reserve inventory, so I'm going from, again, right here, here's the SKU counter going from 1 to 100. Here's the SKU quantity, 1 to 3. I'm basically trying to buy between 1 and 3 of an item. And so I'm doing it for shared state first, and I'm doing it for reactive also. So these 4 requests are happening. so I'm defining a number of threads here in this inventory, in the configuration. So we're going to start with one thread and we'll go up from there. Okay, so this up. All right, so now we start, and now we can look at how long things are taking. Okay, so the important thing here is this average column, and well, it's a little hard to read. I can't make it any bigger. I'm sorry, but essentially what it's saying is they're working at exactly the same speed. Share state and reactive, it takes about 4 milliseconds now per request, and then to reserve it takes about 10 milliseconds, 9 milliseconds. So, I guess that makes sense, right? There's only one thread running right now. There's only one user hitting the application. So, that's not really doing too much. And now if we look at Graphite, I need to change the time range because it's being skewed. When you make this first call to play, it takes a few seconds to it's running through the startup of our application. So it's creating all those actors. It's creating all the inventory. So this isn't really representative. So let me do 4 minutes here. Whoa. Wow. That's a bummer. You can swipe something, whatever you do.
We're just going to be excited.
I know. And you just have to take my word for it. We're going to run them both with a bunch of threads. It's going to be amazing. Oh my god.
Oops. I don't know, dude.
Dana, did you see the speed of light or something?
I may have.
Maybe reseat the download connection.
I tried on my end. Try again.
Yeah, we can check.
Give it a home.
Does the VM come with JMeter installed?
No, it doesn't. But there were instructions on how to do that. No, I didn't install JMeter. It's a pretty quick download though. What were we on? Do you remember?
Well, I just switched it just to see if it was that one. It's not working. I don't know, dude.
That's not.
Nice. I know. Right. To be continued. Okay, let's see. I did.
Did I freeze my computer? It looks like the computer froze actually.
You're running one too many threads.
Just one thread. It's not a good sign, right?
Yeah.
Right. Oh, with the wires.
What's that?
Oh, good. If anyone wants to refresh your drink, grab another piece of pizza.
This actually take that long.
Right, exactly. It's a move for DevOps here. What's that?
What's the tool you're using to generate the
JMeter, yeah. All right, so looks like we're up here. Let's see. Awesome, our dashboard's back up. Okay.
I haven't started running it this week.
What's that? Wait, the graphite should just come right up.
It's like an alternative to
but also type. So in Scala you also can do like and you mix it into a class or an object and then you can set the traits type so it looks like Scala's name consistent.
That's my dashboard.
they figure for them to fail, you would just go back to Java.
What's that? Yeah, yeah. The file. I mean, it's not actually running, but right. Actually, it's the node file. What I can do is going to come up and get it. Okay. Jamie again.
That's good.
Now the only thing that's tricky is I need to actually recreate the metrics. Okay, sorry guys. So now let's go to our test plan again. Okay, so now we're running, we're back to where we were before. We're running with one thread, and now we just need to get our metrics back. So let's go to our dashboard. What's that? Yeah, no, well, this one's okay. This is only running once. Okay, so stats, reactive, get, count, and okay, so so this is going to be a little uglier than it was before because I'm not going to have time to format it. But essentially, I'm not going to bother with the concurrent request. We can get this another thing. So this is so the one on the left here is the reactive application, and the one on the right is the shared state application. And what we can see here is that they're both running very, very quickly. These are millisecond response times. So you can see, it took a second for them to get started. They were running at like about 3.5, 4 milliseconds, 5 milliseconds, and now they're down to about half a millisecond. So this is past 10 minutes, refreshing every 6 seconds. So let's do 5 seconds. Time range 5 minutes. Okay. So all right. So what you can see here is that with one thread, no concurrent access, these two applications are running at a very similar speed, which is not surprising because there's no concurrency, so we don't need to worry about it. And they've just finished, actually. So the average overall was about 2 milliseconds for the GET request, 5 milliseconds for the reserve request. And that's not that exciting. So let's give it a little more load. Let's do 10 concurrent users. So now if we look here, we're starting to see a little bit of a difference here. We can see that the reactive application is taking about 20 milliseconds, and the shared state application taking closer to like 60 milliseconds. So again, not really that revelatory. Faster for sure, but not that fantastic. And if we go look over at the graphs, you can see we're looking at 60, 70-second response times here for the shared state applications. And again, it's hard to read here, but there's dots there. So the one on the left is 2.5 milliseconds, 1.5 milliseconds. Those are running very, very, very quickly. So again, still nothing that crazy though. I mean, we're really not seeing that much of a difference. You can see the shared state one starting to drop a little bit now. It's nothing crazy. So now, let's hit this with even more load. Let's try 100 concurrent users. And by the way, if you want to take we can't look at this, but I'll show you. We're going to start looking at loads of about 200 requests a second when we start getting up to spoiler alert, when we get up to 500 users. This is just my own computer running this, so it's not that crazy. But 100 concurrent users, 100 concurrent threads, so it isn't actually 100 concurrent users, but running as fast as it can. So all right, we start at 100 concurrent users. Now we start seeing some pretty significant differences. The reactive application doesn't change at all. The reactive application with 100 concurrent users, so we're looking at the throughput here. This is concurrent requests per second. We're talking about 90 concurrent requests per second, and it's taking on average 10 milliseconds for requests. And this is with latency. This is with the client going out to the server, getting the response, coming back here. So when we actually look at the okay, So now what we're seeing is, this is again, there's dots there. This is taking 2.5 milliseconds, even less than that, it's dropping right now, taking like, 0.5 milliseconds for the requests that are going to the reactive application. And the shared state application, it's up and down a little bit. I mean, it depends on kind of chance and what's going on with the concurrency there. But we're talking about 400 milliseconds to request now. 400 milliseconds to request that we're looking at for the shared state application. So, all right, so now let's stop this and let's hit it with a lot of load. So let's try, this is like a flash sale. I mean, it's not crazy, right? I mean, just keep in mind, this is just all running on my computer. This is like, I have like my 4 cores, whatever I have. It's a decent laptop. It's mid-2012 though. I could use a new one. I could use a Retina display. Oh, my boss left. So, these 2 applications are both running on my computer. And I don't even think I didn't give all 4 cores, obviously, to this virtual machine. So, just on my computer, we're running 500 users trying to hit my sites here. And now let's see what happens. So now we're going to see the reserve inventory start shooting up. These threads are piling up. They're waiting to get access. As they take longer, there's like the spiraling effect. Look at the reactive application. We're talking about 35 milliseconds, 20 milliseconds now to make these calls. You look at the throughput again. This is so keep in mind here. This is the throughput right now for each request. So actually, you double that, right? Because for the shared state, they're making 200 requests, and for the reactive application, we're making 200 requests essentially simultaneously. So this is 200 requests per second, and the average time here is like 15 milliseconds, 9 milliseconds, versus like 2 seconds. Each request is taking 2.5 seconds now for the shared state application. So again, if we look here at the graphs, this thing basically hasn't changed. This was with like I think this was with 10, this is with 100, this is with 500. We're not seeing any difference really. If anything, it's getting faster. I mean, this is the fastest it's been. Both requests are so again, latency aside, just the processing on the server is taking like less than 1 millisecond for the update operation, and less than half a millisecond for the get operation. And versus now we look over at the shared state application, it's taking 2.5 seconds. I mean, like the latency is the same for both of them. The web server is not doing anything different. This is threads being locked. This is threads going to sleep. This is what happens when you're trying to use like the old school way of doing concurrency. So, I mean, this is the big unveil here. It took a little while. We had a few problems, but this is what you want to see here. This is why you use Akka. I mean, think of if this is what my little laptop can do. What you can do, if you have like 10, 20, like 30 cores, if you have like a farm of these things. I mean, the options are endless, and a lot of companies are switching over to Akka. I mean, there's a lot of benefits to it. So this is extremely exciting for me. Honestly, when I came into this, I had never done this before. I didn't expect there to be this kind of response, but I mean, this is still running. I mean, this is like, we're talking about over like 60,000 requests. This isn't some BS. I'm not like just running it 10 times and like see what happens. This is real. Less than 10 milliseconds to request, including latency for like the reactive application, over 2 seconds for the shared state application, and not changing. This isn't going to change. And again, look at the errors. There's no errors. This is just doing what it's supposed to do. 200 requests a second, bang. So so that is my presentation. And I actually turned off my PowerPoint, so I'm going to back up. Just to remind everybody that we're hiring and that we're looking for good developers. Where are we? Here we go. Okay, so now it's time for Q&A, and I'm happy to answer any questions at all. Yes, Greg.
Quick question. You have a slide with the GitHub page. That one of your slides? Yeah.
So that's the next slide. That's right. The last slide, and I'll also post this to the meetup. My Twitter handle is our HBC's Twitter handle, LinkedIn. My email address. Please get in touch with me. I'm happy to talk to anybody about anything. My Twitter handle at the bottom. There's the repo. It's totally. I think maybe the deck has changed slightly, like since I last did it. But yeah, yeah. So yes,
You open that one up, you open that repo to the public.
it's completely public. Yes.
Okay.
I think if you're ever out of a job in dev, like you can be a NASCAR announcer.
Yeah. I get excited about this stuff. This is like really exciting stuff. This is fun. Like this isn't like, you know, I've had jobs where I didn't enjoy what I was doing. When I'm working for HBC, I look forward to coming into work every morning. We get the opportunity to play with like tools like this. This isn't like every company that gets to do this. I mean, this is enjoyable for me. You know, I look forward to coming in Monday morning. I have 3 kids. By Sunday night, I'm like dreaming about getting into my office and playing with like Akka and like leaving my family behind. Yes. What's that?
Akka system got dead letters.
So dead letters is essentially where all the messages in Akka go that don't have anywhere to go. So yeah, you saw there that was sort of some error handling there. I mean, so obviously next steps would be to build up more error handling. There's a million different things that could be done if this wasn't a Tor application. But what I was saying there is, if for some reason someone made a request for a product that doesn't exist, then basically here's the actor that you can send, you know, these messages to. And if an actor dies, it'll go there. That's kind of like the backup place for messages to go.
Like MQ.
Yeah. Great. Other questions?
Yeah, Dave, I have one.
David.
When you were developing this, and you saw the unbelievable numbers the Akka side was producing for you,
Right.
did you make any attempt to go to the shared state side and try to prove it? You just gave
I did. I actually wasn't sure that this was going to happen. And I actually initially used, Akka has a streams library that's a bit experimental, and they have an HTTP server built on top of that. And I was using that initially for the Akka application because I thought it'd be cool to use Akka all the way through. And it was not working very well. So I was a little scared. I was like, maybe my assumption's wrong about Akka being faster than Threads. So I was the opposite. I was doing everything that I could. I was like, okay, maybe we shouldn't have dirty reads on the shared state side. And maybe, you know, we want to make sure, you know, I kind of was trying to twiddle it a little bit because, you know, when I came here, I wanted to have something good to show you guys. You know, I'm not above a little bit of trickery. So then when I actually switched to play and I saw the numbers, I put all that back. I made it identical. Things like where I'm sending the metrics via futures, that wasn't happening initially on the Akka side because it's easier just to do it inside the actor. Everything that I could possibly do, I made exactly the same on both sides. I did everything I could possibly do. And I did, like I said, I allowed dirty reads on the shared state side. I was using a reentrant read-write lock initially, which would prevent dirty reads. I switched just to locking just for writes. I did everything that I could. There's nothing else that I could change here. I mean, I tuned this as much as possible on both sides. So yeah, the answer is this is the best I could do. I mean, it's so simple, right? I mean, and I was also thinking about, well, maybe if I put like a sleep on both sides, like that would, you know, when I was worried about it not working, maybe if there's more processing happening, then the threads will start piling up. None of that's happened. This is all just the application. All it's doing is reading one piece of mutable state, and this is what happens. Thank you. Yes. Anybody else?
Is there any other comparable libraries to Akka? Different languages?
Yeah. So Akka, the inspiration for Akka, correct me if I'm wrong, was it? Yeah, Erlang was kind of like the inspiration for it. You know, there are other actor frameworks, you know, out there, but nothing that I've actually used extensively. Yes, go ahead.
When you're updating and getting the product inventory level, are you using the same product ID repeatedly?
No.
Process, or are you running?
So it's going. So JMeter has an ability to create variables. So it's going from 1 to 100. It's shooting through every single one of the 100 inventories in sequence over and over again for each thread. So yeah, I mean, again, you know, I mean, right. So in a real estate, probably gets would happen more often than updates. You know, there's other things. This is obviously a Tor application. Not the disclaimer. You know, these results aren't guaranteed for your e-commerce website. But you know, yes, like we try to get it as close to real as possible. Anybody else? I mean, so this is our, as I say, our obligatory we are hiring slide. Please, if you're interested in doing things like this on a daily basis, working with really amazing developers, you know, working on an amazing stack, this is the place for you. And I will post that link to the meetup page, and you are welcome to do whatever you want to it. Pull request, please. And
Yes.
and if any other questions come up, if you have any issues or anything, please let me know. I'm happy to explain it further. Discuss anything with you. This is a passion for me. So I find this very entertaining.
And if you want to work here, my business cards are on the table at the check-in desk. So shoot me an email. Thanks everybody for coming so much. Great.
Everything worked out.
Christian.
Should have.
Did it record? Maybe.
Yeah, I should have recorded. Should stop it.